Hello and welcome. In this lecture, we're going to be talking about 3D printing. This is a video that is for those of you in Machine Shop Lab. If you are in additive manufacturing, you could certainly watch this, but it'll be certainly more relevant to you if you are in Machine Shop Lab. Okay? And this will sort of serve as a general overview, and then later on in the video, I'm going to go over how to make the CAD and everything like that, so that you could go ahead and make the part. Okay. So yeah, we're going to talk a lot about the stuff that is available at school today. What I could also throw in this video is how to submit a ticket through the ticketing software system. All right. So yeah, basically the technologies we have FDM, SLA, PolyJet, and SLS. FDM stands for filament deposition manufacturing. SLA stands for stereolithography. PolyJet is not an acronym, but SLA stands for selective laser sintering. So let's go over those in a little bit more detail. So FDM printers, this stands for again filament deposition manufacturing. So basically, what happens is there's a solid spool of material that gets fed through a nozzle, and can melt the material in sort of a quasi-liquid form, such that it doesn't flow out everywhere, but can sort of be placed somewhat precisely and controllably. Yeah, and then that layer that was placed down soon cools, and then another layer can be placed on top of it. Okay, this is one of the older technologies. Believe it or not, the oldest technology is SLA. But yeah, they have been around for a long time, and so they're pretty cheap these days. In fact, more recently, these printers have been, sort of a race to the bottom among like the competition. So just basically try to make these things as cheap as possible, which is nice because they've worked their way into, the homemaker space. So that's kind of cool. A lot of times, if you buy a hobby 3D printer, this will be what you buy. Okay. With this printer, the resolution is controlled by the nozzle size, okay, and its layer height. All right. So basically, if you have a really, really fine nozzle, you could create much finer features and things like that. Yeah, you're limited because, with plastic, as you like, send it through like a small nozzle, you can only really go so small before you start having like extrusion issues. So yeah, generally these have less resolution than some of the other machines we're going to talk about. But yeah, it's still pretty good, especially if you get smaller nozzles. But what's kind of unique about these machines compared to like some of the other ones that I'm going to talk about is the ability to control your infill. Okay, so there's a lot of settings that you could go through with your slicer. You could change your wall thicknesses, but what's very commonly changed is your infill percentage, which will allow you to change, strength properties of your part as well as control the weight if that's what's actually needed. So yeah, it's kind of interesting. It also is a good way to save material. Although the material for FDM printers is often the cheapest, it's often helpful to add a sparse infill so that it can be even lighter still and, the correct weight, based on your specifications. Okay. Again, I told you this has less resolution. Usually with 3D printers, there's a trade-off, however, for resolution and build volume, or resolution and some other quality usually. But yeah, usually these have the largest build volumes of any other of the like, readily available printers of the other technologies. The largest one we have is going to be probably the Prusa XL, which is 14 by 14 by 14 inches. So pretty big. But yeah, another advantage of this machine, or of this machine type is the ability for like a lot of different types of materials. And yeah, you have a lot of, I should say you only have thermoplastics that you could use for these printers, which are plastics that liquefy when they're heated to a certain temperature. You have thermosetting plastics, which are by means of go from liquid to solid by means of some chemical reaction, and they're not really that reversible. But yeah, so you could use PLA, PETG. PETG is basically the same stuff that comes in Coke bottles. You could print nylon. You could print onyx, which is a variation of nylon. I'll talk a little bit about that on the next slide. And lots of other stuff like TPU and other flexible materials, and various things like that. Okay. So yeah, next slide here. These are all the different types of FDM printers that we have. So we have basically a lot of our workhorses are going to be these Prusa Minis. We don't have the Mark IVs. We actually have the Mark IIIs, but they're a little bit yeah, they're only just a little bit bigger than that one. So yeah, basically the same thing as that Mark IV. And then we have one of these XL units. Okay, so these are predominantly the workhorses. We used to have some Ultimaker Cura S, yeah, Ultimaker S5s, I should say. But yeah, the Prusa Minis work pretty well. The a couple of different nuances in the technology. As you can see, the Mini here, as well as the Taz, the Lulzbot Taz up here. They're both like what they call bed slingers, which means the y-axis is on the bed travel, and the x-axis is on the gantry above, as is the z. So x and z, mean the nozzle is moving, but the y-axis mean the bed is moving. So yeah, there are some disadvantages to that. It can be a little bit cheaper to sort of make that configuration. But basically, it could also lead to some wobbling issues because the bed is what's moving and that's where your part is. And so if your part is not, completely fixed, then that can lead to some issues. But the Prusa XL, the big one that's over here, and the Mark Forged Mark II are both Core XYs, which means the X and Y's control is, the nozzle is moved in the X and Y, and the bed or build platform is only moved in the Z. Okay. Talking a little bit more about the XL, as you can see, it has multiple extruders, so you could do multiple colors and multiple materials, so you could print in a support material that is different to that of, what the main part is. Okay, so that's pretty nice with that one. And all of these are different extruders, so there's no purge cycle, which is helpful when you have a really long print with a lot of color changes. Okay. The Mark Forged here, this was honestly my favorite when I used to work in the Idea Sub. But this has the ability to print that onyx material that I talked about before. So a little bit more detail about that. The onyx material is like, basically a spool of material that is nylon with little flexicarbon fiber sort of built into it. Okay. And that's really cool because it makes the overall material very tough. Okay. And in addition to, just the filament being tough, you have the ability with this machine in a different extruder, so dual extrusion. I guess you can't really call it extruding because it's not melting anything, but it's able to feed in carbon fiber, okay, which allows you to lay in continuous strands on different planes, okay, which is much stronger than just having little flecks of carbon fiber that are non-continuous. Okay. So yeah, pretty cool capabilities in our machines. There's a couple of other ones floating around, but these are the main FDM printers that we have. Okay. SLA again stands for stereolithography. Okay. The way this one works is basically you have a build platform that's upside down and it sort of lowers into this vat of resin. And really, I guess what I should be calling these slides are, vat polymerization printers. That's sort of like the higher category. But most of them are SLA. We only have one vat polymerization printer that is not SLA. But basically, SLA specifically means you have the laser that comes from underneath and cures the resin, where a lot of other vat polymerization printers will use like an LCD screen with like, UV pixels, basically. And, it's able to turn on different pixels on different layers to show which to print out your entire form, and the laser basically just shines on different portions of the part, and allows different portions to cure, and yeah, and it forms your part pretty similar way. Okay. These have really high resolution. Yeah, your resolution these days can, is kind of more limited by the material rather than the screen and or laser or optic point that you can create. So yeah, these are really good for high resolution stuff. They can be kind of slow. For the reason that it can only create solid construction. So with FDM that we talked about, it can only make parts, it can make parts fully solid, where the entirety of the inside of your part is solid infill. But yeah, these SLA parts can only make stuff with solid infill. So you wouldn't be able to save time and sort of save space inside your part. Okay. Which is okay a lot of the time. You could sometimes design your way around it, knowing that you're gonna have a solid part and you'd make thinner walls and things like that. So you could somewhat design your way around it, but yeah, you're limited to only solid construction in this. But with this, you also have a wide variety of materials. For us, we have a lot of the Form 2 printers and Form 3 printers and Form 4 printers. And Formlabs has a really, really good library of like statistics and data from all of their resins. Okay, so as you're designing things, you can know exactly like what the material strength of your pieces would be. Okay, and they could print a lot of things that are like in the rigid plastic forms through a bunch of different types of like biomaterials and flexible materials and many things like that. Okay. So yeah, these are our form printers. As you can see, the print is held upside down and dropped into the vat, and then sort of pulled up through the vat, like or yeah, through the liquid like that, and each layer is formed. So pretty cool. Yeah, it has sort of scaffolding supports that sort of hold it on from above. But yeah, basically, as you can see, the part in this Form 2 print here, it lowers down onto the vat that's underneath. That's where the liquid resin is sort of dispensed. And yeah, drops down. The screen is underneath the sort of orange hood here. Is where all the like moving components for all the optical stuff and the power for all that cures your part. Okay. Again, our Form 2 and Form 3. Form 2 is the smaller guy here. Our Form 2 and Form 3 are true SLA printers, meaning they have a laser head in them. But our Form 4 has an LCD display, basically like a screen that has really high resolution. I think it's an 8K resolution screen, and it can cure in very specific spots where it needs to be. So yeah, cool capabilities. Next technology of PolyJet. This is also a photo cure resin, but instead of the build platform dropping down into a vat of resin, basically resin gets dispensed through what are basically inkjets onto your build platform. And then as the head, moves across the build platform, dispensing the the plastic, a UV light is basically right next to the inkjets and dispenses and cures the resin that is just dispensed. Okay. These have really fast print times. They have really high resolution parts. But I would say they lack in terms of the material strength properties. So if you are using these to do something like create a prototype that's aesthetic only, or do things that are true to have very true resolution, but not necessarily high strength properties. These could be a good solution. Okay. It also has the ability to combine two types of materials. Okay, so there are plenty of these machines by Stratasys. That's the company that we have that have 8 material bays that you could put various different colors in them. And with these liquid materials, you have the ability to combine streams of resin in variations so that you could create either specific colors with two different colors or in our case, you can combine a very rigid material and an elastic one, and you could sort of tune the durometer or softness of your part according to what you want it to be. So it can be kind of a cool prototyping tool. I would say that even, when you try and tune a part and make it, say, more ductile, it still, it still has a tendency to crack. And even if you make it very, very flexible, I find that it likes to tear a lot too. So it can be very valuable, but generally, I don't like so much the PolyJet printers. Okay. Or sorry, or at least the PolyJet materials, I should say. I'm not a huge fan. But yeah, just some examples of some PolyJet parts. As I said before, you can sort of tune the durometer or tune the part. So you see, you have some portions of these parts are black, which would be fully flexible, and then some sections are white, which would be fully rigid, and then some of these are gray, so they sort of tuned it somewhere in between. Okay, and in addition to being able to make, you know, a certain part, vary from hard to soft. You could have certain sections of a part that are assigned to be rigid. Oops, sorry, gotta go back. Certain sections of a part that are designed to be rigid, certain ones that are designed to be completely flexible. Okay, so a good example of that, when we sometimes print the steering wheel on those machines, if not just for a prototype. But you could print the rigid portion in the white stuff, and then you have just the grips in black, so you have like a soft grip to grab onto. So yeah, lots of applications for that. But yeah, again, I don't super rate the material. This J35 is kind of interesting though. Instead of having a build platform and a head that moves in the X and Y, basically the build platform rotates, okay, and goes up and down. So it just continually spins around, and then the unit moves in the radius direction. Okay, so basically it doesn't need an X and a Y. It has an X and a Y and a Z. It has a Z and a theta and R. So kind of interesting. One of the secrets to it being able to print so fast is it, being able to continuously spin. What it does kind of mean is you can't necessarily like use the whole build volume. Like you can't put anything across the dead center. So there are some, I guess issues with it, but overall, it's a pretty cool machine and really good for very basic prototyping that doesn't need any load requirements. Okay. Finally, we have selective laser sintering. Ours is a plastic laser sinterer, but there are other ones that sinter metals and things like that. Yeah, basically you have a layer of powder that's set down on your build platform, okay? And then a laser comes and binds together all of the portions that will later become your part, and then it lays another layer, okay? Critically, it doesn't do anything to take away the loose, powder, that was non-sintered, because that becomes your support material. Okay. Which is really interesting because then you're able to recycle it, which is nice because this is the most expensive, material type that we have more or less. You can't necessarily use it as like a 100% recycle sort of thing. They basically, after you take it, after you remove it from the part, after something is printed to be, recycled, it gets a little bit clumpier. So they like that you mix it in with some new powder, just so that it's a little bit smoother to be dispensed in the machine. Okay. But yeah, for the most part, yes, you can basically use, all of your, unused support powder, again, in another print, which is helpful. Another helpful aspect of having the powder be its own support is the fact that you could utilize the full build volume. Okay. So, having it so that the entire volume is already getting like filled with this powder, okay, means that, you have very reliable support basis. You never really want to, on an FDM machine, stack parts on top of each other and utilize the full build volume. You're probably likely to run into failures. in terms of like not being able to support or under extrusion or something like that. But this is really good in that like it lets you use the entire build volume, which makes it, really fast if you're a student worker in the Ideas Hub, to just set up a bunch of prints and have everything run, on a daily or twice daily basis, depending, on how many you could fit in there. Okay. The material is quite expensive, even though you can recycle it. So yeah, you should use wisely. Anyways, um, these are some examples of stuff you could print in the SLA. So these shoes would be an example of something that would be really, really hard to have like conventional support and then remove it. With the foreign printers, you're going to have this like scaffolding on the inside that would be hard to like snip clear of all those voids and openings, in those shoes, for instance. So the SLA powder is really, really good if you have like really fine crevices and things like that that would be hard to remove support from. Okay. So yeah, very yeah, a lot of pretty good capabilities that we have here in the Ideas Hub. So yeah, you definitely try and utilize these when it comes to senior design. However, with this class, we are going to just focus on running ourselves a pretty standard and basic FDM printer that we have in the machine shop, which I'll go over later in this video. But now what I'll do is I'll transfer over to SOLIDWORKS and talk a little bit about how I did the CAD for this project. Okay, so moving over. Okay, so here we have the Machine Shop Lab project. Okay, as you can see, in the middle here we have the actual track part of our marble maze, and that's what we're going to be 3D printing. Okay, so I'm going to go over how to make this. So I'll quickly open this up. Okay, so this is the marble maze by itself. So I'm not going to go over step by step how I did the CAD, sort of, at normal pace, but I will go through the tree view. So the first thing I do is I create a sketch that sort of outlines how big the part is and what the increment of the zigzags are. And then what I do is I create a bunch of planes that sort of separate where the individual platforms will go, or sorry, I should say the switchbacks. So where these U-shaped portions are, and also where the inclines are. Okay, and then I create a 3D sketch. So that's that portion there that links everything together fully. And then from there, I'm able to make this sweep from it. So if I go in, I could edit the sweep. Okay, and I've selected the 3D sketch that I made as well as this profile sketch. Okay, so quickly go into that one and show you how I made that. So yeah, you can see I use those increments. You could use something similar to those if you want. That's probably pretty appropriate to keep a small marble in there. Okay. And then after that, basically what you do is you make a bunch of platforms. So with the first platform, I think my initial idea was to make these rectangles that were to be extruded into the part, but I had a lot of merging issues with those. So what I ended up doing was, creating a sketch that sort of went around the switchback and then sort of extruded them into each other. You could see the profile sketch for this one. As well as some of these other guys like that. So yeah, you can see there's the sketch that I ended up making and basically just extruded it into the switchback. Okay. And basically I repeated that process for all the other ones. And also added a bunch of different hole types based on the specifications that I needed. So I had some tapped holes going in on the sides here. Got a counterbore hole coming from the top, two coming from the bottom. And yeah, I won't go over all the exact holes that I use and why. But basically the key to this is basically that sweep and then, making a series of extrusions that go into that sweep that, allow for it to be bolted to something like the 3D printed part or one of those other guys. Okay. So yeah, that is about it for the model. We will save this as an STL. Okay, so I'll go File, Save As, do that. And then I'm going to make this an STL down here, and that's the going to be the format we need for the 3D printer. So, yep, I'm going to just override this and save it. Yes. Okay. So, and yes. Okay. All right. So now what I'm going to do is I'm going to open up Cura here. So this is Ultimaker Cura. Yeah, you could go and download this. You just type in CURA Ultimaker Cura, and you can just get the most recent version. I'm not going to be super specific with how you need this print to act. If you'd like to do it, I guess, in a different slicer, you can do that as long as I know that you've created G code for this print. I'm happy, and as long as the print comes out, then I'm also happy, you know. And if you really wanted to slice it on something different and still print it on the FDM machine I have, that is cool. That is cool. I don't want you printing this in the Ideas Hub. That's not something I do for this class anymore. A while ago I did. But yeah, basically, as long as you slice it yourself and run it yourself on the Ultimaker, or sorry, on the Ender 3 V3 SE that we have in the shop, then that's totally fine. Okay. So yeah, let's go to Prepare tab. Let's make sure the correct printer is selected. So again, we have the Creality Ender 3 V3 SE. So I could show you where that is. If I go to the Add Printer, Add Non-Ultimaker Printer, Add Non-Network Printer, and I could go down to the Creality 3D, and that would be the Creality Ender 3 V3 SE. I could select that one, but I don't need to select it because I already did. Okay, so now let's take a look and let's put in the 3D printed part that we just made. Okay, sticking that guy in there. So as it happened for me, this is kind of nice and lucky that this is the orientation that we're going to want to print in. So yeah, you know, basically what you're trying to do usually is, for one, achieve all the resolution stuff that you want, and print in a reasonable time. And you know, a lot of times also you want to be thoughtful of where your support is actually going to be needed, you know, versus not needed. Because if you can avoid putting support on parts that don't need it, usually you get a better resolution and less post-processing that's needed afterwards. Okay. So yeah, let's talk about your different settings that you have here. So over here, I put it in. This might look a little bit different on mine than what it does on yours. But basically, I tried to put it in the basic settings here so that hopefully you guys could navigate through this as I'm talking through it. So you have layer height. This is, you know, how much the printer will move up in between layers so that it you know, it's every layer it deposits new resin on top of, you know, the previous layer. So this basically tells the server how much to move up each layer. Okay. So yeah, right now I have a wall thickness of 0.8 millimeters. Okay. Yeah, and basically I could set my top and bottom thickness. I'm making those the same value in this case. Doesn't really matter. And then my infill density, I'm making that 20%. I think I have in the rules, I think I have you doing triangles actually. So I think that's what we'll stay with. And then I recommend you bumping up the temperature to 210 for the nozzle, and the temperature for the bed move up to 65. That's often helpful. And then support material, you generate support. I did the normal support, and I'm generating support. And instead of normal, I could do tree. So let me show you the different nuances. The blurb that shows up is kind of helpful for this. But yeah, you could see that the normal support kind of goes directly underneath the part, and supports it sort of in a mathematical way. The tree support is a little bit more organic, and it supposedly cuts down on the amount of support that you need, and you could touch that, tune the touch point size to where the support, is easy to get off and things like that. So yeah, cool things you could do with the support, but we could just probably keep it as the normal support. As for build plate adhesion, we'll leave it as the brim. Come on, show up again. There we go. So as you can see, there's three main types of like the build plate adhesion. So you can make a skirt, which I don't even really classify that as a bill plate adhesion structure, because it's not attached to the part. Basically the skirt kind of just serves to purge a little bit more, in my opinion. Okay. The brim, however, since it is attached to the part, effectively increases the surface area that it's touching. That the part is touching the build platform with, which usually increases its stability. Okay. And then you have raft, which is, arguably the most stable of all. So, basically it builds up a layer of this raft material, so that hopefully, when your print starts, it has, a perfect initial layer to start on, and any sort of first layer weirdness, can be avoided. Okay. But yeah, we're just gonna do the brim. I think that'll be more than effective for this one. If you add the raft support, then it can take like a little bit too long on that first layer. Okay, so now let's slice it. I'm going to X out of this menu here. All the selections are still present, but I'm going to slice it so that we could sort of see what it's doing. Okay, so under preview now, so you can see it's going to take 15 hours, 34 minutes for pretty standard. All right, and this is basically what the G code will try and make. Okay, so you can see where all the different layer lines of things are, and this is kind of a simulated view of what it's going to look like. And what's kind of cool is I could drag this down on the right-hand side, and I could expose the infill structure. Okay, which is kind of cool. So you can see here, in this portion of the part, it's not going to do the infill pattern because the walls are kind of too thin. But over here it will, because the part, cross-sectional thickness gets greater on that cross-sectional plane. Okay, cool. So yeah, you could scroll through and you could see what it's doing on all the different layers. So pretty interesting and somewhat helpful at times. So you could see where it's doing what, when, and where the wall thickness is on various parts, and it's all from a visual standpoint. Okay. So what I kind of don't like about this, so I'm going to open up the menu again by clicking this tab here, the standard quality 2.0. If you just click on that, you get your fancy menu back. But what I'm going to actually do is change the support overhang angle. So you usually want to avoid support going inside the track if you can. And the way I made this track, it's not like severely overhanging, like an overhanging cliff, too much to where I will need it. Now, certain 3D printers, especially the newer ones that are a lot better, can handle doing a fully overhanging portion, but just for short spans, kind of. Okay. I'm not confident that this span, the one that goes like say from where my mouse is now over to there, that span there, I don't think that will succeed if we don't have support. However, the inside of the track here, we can try and avoid. So basically the support overhang angle is a little bit confusing, but it's all taken from vertical. Okay, so if this is 0 degrees, this is a 90-degree support angle. So it has to support underneath, angles of 90 degrees. So instead of 45, so basically 45 means it supports it if it goes 45 or greater from vertical. Okay, so if I make this, I think I made it 80 before. Yeah, so we changed it, and obviously our preview went away because we have to reslice it. So let's do that once more. Okay, cool. A little bit less time, which is nice. And now the track inside is support free. Okay, or at least apart from that little portion there. And I could try and tune that, but I'm not super worried if it's in there a little bit. Predominantly most of this track is going to be is going to not have support print on it, so it'll be, easy to clean out in that way. Okay, so I'd be pretty confident with running this. This seems like it'll work quite well. Again, we're supporting the track at its most vulnerable point, which is at this point here or at this point there. Okay. So yeah. Now we will save this onto a disk or hard disk. So got a little flash drive here. You could stick it in. Where's my port? Okay. Upside down. There we go. Sticking that in like that. Okay. It's gonna show up for me. And then I have the option of saving to the removable disk. File saved. Okay. I could eject that and now I could go to my printer. Once you've sliced your file, you could come up to the machine. Okay, so this is again an Ender 3 V3 SE. This is my one I have at home, but it's exactly the same as the one in the machine shop. Okay, so you take your flash drive. You actually got to stick it teeth up into the machine on the side over here. Okay, so you stick it in there, and it'll click in and stay. Okay, and then on the screen here, you should be able to navigate through it. So yeah, so you have four options initially, and so you'll go to print, and then you'll go to the file that you want. You can select it, and yeah, so I'm gonna actually put the calibration on, so you make sure that the bed leveling is on. Make sure the build platform is free of any debris or anything like that. And then I can go to confirm, which will start my print. Okay, so it'll start out by doing a bunch of limit switch stuff, and then eventually, finally start printing. So I won't bore you with all that. But yeah, I would encourage you to stay around for maybe the first layer of your part just to make sure that it's successful. Because again, this doesn't really have any monitoring systems to tell the machine whether or not a print has failed. You're basically supposed to tell it to stop if it fails. Okay, so be aware of what the machine is doing, and you can leave once the first few layers are successful. Then you should be pretty confident that the rest of the layers are going to go smoothly.